In this video, we'll be going over rotation and angular momentum. A round cylinder has a moment of inertia I is equal to 2 over 3 mr squared and is released from rest at top of an incline tilted at theta degrees relative to the horizontal. The cylinder rolls down the incline to the bottom, a distance d, without slipping. Draw a free body diagram of the forces acting on the cylinder with vectors originating at the point of application. So, for our ball, we have gravity, mg, acting down. We also have normal force at the point of contact, but we are at a angle, so that is going to look like this relative to our axis. Now friction is going to act up the incline. And what friction does, this is rolling motion. So friction provides torque for rolling at your point of contact. Determine the acceleration down the incline. You can use linear force. We know that parallel to the incline, the summation of forces will equal to the mass times the acceleration. We know that mg sine theta minus ff is going to equal to ma. ff is, we know that the summation of our vertical forces equals to 0 because there is no acceleration in the y direction. And we know the summation of forces in the x direction is also going to be changing. So we need to find the acceleration because the acceleration does not equal to 0 because acceleration is changing. So that is why we have only our horizontal forces here. So our friction is acting this way up the hill, and then down the hill we have this force. We can draw out the rest of our FBD here actually. That is Fn. That's mg, Fg. This is going to be our theta. Our acceleration direction of motion is down the hill. And we know that this is our theta because that is our theta. So this makes this parallel component to the incline equal to mg sine theta. And this vertical part is mg cosine theta. The reason for this is because sine is equal to the opposite over the hypotenuse, and this is the opposite, and we also know our hypotenuse, which is gravity. And here we also know, using a triangle again, we can form a second triangle like this. And we know by alternate interior angles we know by alternate interior angles that this is also going to be theta. this is, let's label on both of our triangles. So the opposite side is this, the opposite side is this. Our hypotenuse we know is going to be this. So here we're given those values. In order to find this length, you use sine of theta and multiply it by mg. Here you have your hypotenuse again, and you multiply it by opposite. And then here, this is your adjacent side to your angle, and this is also your adjacent side, which is why that vertical part is mg cosine theta. So that's how we get those values in our equation. Now, moving back to torque, we know that when we write our torque equation, we know only friction causes torque. So you can write torque is equal to your moment of inertia times your angular acceleration. Now, you can write your torque from friction. So your torque is going to equal to your lever arm times your force of friction. Therefore, you can write that R times your force of friction is equal to your moment of inertia times your acceleration. Which this is just one string. Now, we can apply the rolling condition. This states that acceleration is equal to the lever arm times the angular acceleration. Angular acceleration is equal to the linear acceleration divided by the radius. If you substitute this into the torque equation, so our torque equation is this, and we want to sub 2 into 1. So you have that Rf of f is equal to your moment of inertia times your angular acceleration, which you found, which is your linear acceleration over r. Now, after this, you can write this as dividing both sides by r. That's in the multiplication in the denominator, so this becomes f of f is equal to your moment of inertia divided by r squared times a. Now you can plug in your moment of inertia. Our moment of inertia for a solid sphere is going to be 2 over 3 r squared. So now this is going to be f of f is equal to 2 over 3 r squared over a. Now you can just cancel out that r squared. F of f is equal to 2 over 3 a. Now you have f of f, which was what we needed. With f of f, you can sub this into our equation over here. So we can rewrite this. Instead of f of f, we plug in what we just got for it. Okay. Now we have minus 2 over 3 a is equal to ma. Now we just solve for a. We want to get a. So we have mg sine theta is equal to ma plus 2 over 3 ma. You have mg sine theta. And you can also write ma. You can write 1 is equal to 3 over 3. It's also equal to 5 over 5. Anytime you divide something by itself, it's just 1. That's how you represent a whole number as a fraction. So you can rewrite that as 3 And then you can just sum those two fractions. So that's going to be 5 over 3 ma, because it's the same thing as multiplying by 1 as well. You can cancel out your masses now, and you're left with g sine of theta is equal to 5 over 3 times a. After this, you can multiply by the reciprocal, so both sides. And then after that, that's going to cancel, and now you just have your a is equal to 3 over 5 g sine of theta. And that is our a. Determine the maximum coefficient of friction necessary for the cylinder to be able to roll without sliding down the ramp. So this is our cylinder. Oh, this is actually, this is a cylinder, not a solid sphere. Determine the coefficient of friction necessary for the cylinder to roll down without slipping down the ramp. First, you're going to use the definition of the coefficient. Because this is friction, you can use mu, and that's the coefficient of friction. F of F over N. We know this because F of F is equal to mu times N, your normal force. Now you can find the friction force. Earlier we had that F of F is equal to 2 over 3 m times a. Now if you plug in your acceleration, you have 2 over 3 m times 3 over 5 g sine of theta. Now that's going to equal to, canceling out that 3, now you have 2 over 5 mg sine theta. Now, in order to find your normal force, you know your normal force is equal to mg cosine of theta. And the reason is because f of y equals to 0, and there is no vertical acceleration because the mass is only sliding down. It's not sliding, it's rolling down the hill. It's rolling downhill. It's not going through the hill. If it was going through the hill, there would be vertical acceleration too, but there's enough normal force to keep it, you know, just like, there's enough normal force that keeps it above the surface and not like falling through the incline. So that's 2 over 5 mg sine theta. Now after this, we can plug this into our equation because now we have both f of f and we also have your normal force. So mu is going to equal to 2 over 5 mg sine of theta divided by mg cosine of theta. Now if you cancel out mg, you have that 2 over 5 sine theta over cosine theta is your answer. But this is a trig identity, which is tan theta. So you can rewrite this as 2 over 5 tangent of theta is equal to the coefficient of friction. In addition, you know that what we have is gravity downward, normal force perpendicular to the surface, and friction along the surface. So you might wonder, why does friction point up if the object is moving down? Well, something that may go against what you already know is that here friction does not oppose motion. what it actually is doing here is it opposes the relative slipping between surfaces. If there was no friction, that would mean that gravity pulls the cylinder down the incline. That means the center of mass would accelerate, but there's no torque. That's because Fg is at the center of mass, and when it's at the center of mass, then R is equal to 0. So that means that torque is equal to 0. Therefore, it would slide. And also the bottom would slip backward relative to the surface. Now, what is the bottom of the wheel trying to do? Well, on the bottom of the wheel, what we're gonna have is that as your center of mass accelerates down, the bottom of the wheel wants to slip down the incline relative to the surface. So what happens is that the surface, it must prevent slipping. And then the direction that the friction has to act in order for the friction to stop the slipping, it must pull up the incline. The cylinder rolls along the horizontal surface without slipping and encounters a second plane incline at theta degrees as shown. The coefficient of friction between this plane and the cylinder is less than the value determined in part C above. Will the maximum vertical height reached by the cylinder on this plane be more, less, or the same as the first one? So basically this ball is going to roll down this incline, and then after it rolls down, it's going to travel a distance and then roll back up this second incline. So we're asked whether this vertical height that it reaches will be more, less, or the same than over here. So we have to account for the fact that we have friction, and we also have to account for the fact that we have, or whether we have or we don't have, conservation of mechanical energy in both of these situations. So first, let's examine the first incline. So for the first incline, we have rolling without slipping, and when we have rolling without slipping, this means that you have energy conservation, because all the mechanical energy will remain mechanical in the entire system because of the fact that we have rolling without slipping. And when you have rolling without slipping, it means that the point of contact is instantaneously at rest, and the friction force the static friction force does no work, and it does not, and this prevents the dissipation of energy into heat. And that's because the point of contact keeps changing. So imagine this, like each time you're rolling, it's instantaneously at rest, which means that each of these points, those are the points where the friction acts. And then after that, the point changes as it rolls around. So you can imagine this is just like going around. So this is one point it's at contact with the incline here, then here, and then here, then here, because it's rolling just for a brief moment. So Now on the other hand, for incline 2, we have rolling with slipping. And because we have rolling with slipping, this means that Fk acts, or kinetic friction force. And that means some of the mechanical energy is lost as heat. So that means that your initial mechanical energy is going to be greater than your final mechanical energy. And if you have less total energy, that means you have less gravitational potential energy. So because of that, we know that when you multiply mgh in comparison to your new one and your old one and your original one is going to have more of a magnitude because of the fact that your total energy is going to be less. Your total energy is going to be more. And then that's because energy is not conserved, because you have friction acting. And because it's slipping, that means that it's not instantaneously at rest. That means that the friction is dissipating the total energy from the system. So because of that, we can see in MGH, comparing these two MGHs, we can see that the max vertical height is going to be less in the case of our new case. So let's look at our E. Will the magnitude of the angular acceleration of the cylinder as it rolls up the incline be more or less or the same as the first one? Explain your answer briefly. Okay, so we can remember that from our torque equation, we know that torque is equal to moment of inertia times the angular acceleration. And we know that torque is caused by friction. So we know that torque is equal to the lever arm times the force that's perpendicular. And we know that from rolling, earlier that we found that the force of the friction that is static is equal to 2/5 mg sine theta from rolling. Now, let's look at our second incline. We know that in our second incline, we have that the frictional force that is kinetic is less than the frictional force that is static. And that's because static friction has to be overcome in order to start moving. So now, that's how we know that the mu actual is less than the mu minimum. So therefore, f of f is going to be smaller. And we also know this from this relationship here, which shows that if you have a smaller torque, that's going to result in a smaller angular acceleration, because your angular acceleration is directly proportional, it's like the same symbol, to torque. A long thin rod of mass m, which is equal to 0.5 kilograms and length L, 1.0 meters, so 1.0 meters and mass 0.500 kilograms, is free to pivot about a fixed pin located at L/4. The rod is held in a horizontal position as shown above by a thread attached to the far right end. Given that the moment of inertia about an axis of rotation oriented perpendicular to a rod and passing through its center of mass is 1/12 ml squared, determine the moment of inertia I of the rod relative to the pivot at L/4. So we know that we can use the parallel axis theorem. Which states that the I is equal to the I of the center of mass plus m distance squared. So first we have to find the distance. D is the distance from the center of mass to the pivot. What is that distance? So we know that the pivot is at L/4, and the rod's center of mass is at L/2, and we want that distance. So this is going to be equal to L/2 minus L/4, which is just L/4. Now that we have that, we can plug this into our parallel axis theorem. So let's get this L/4 here, D. I is going to equal to 1/12 ml squared plus m times L/4 squared. We were given this I as our moment of inertia, which we plugged in right here, the center of mass. Now after this, we can expand the second term. So we know that's going to be equal to ml squared over 16 l squared and then 4 squared. So then that's going to equal to 1 over 12 ml squared I. Now we can combine some fractions. We know that 1 over 12 is equal to 4 over 48, and we know that 1 over 16 is equal to 3 over 48 l squared. Now, if we combine that, that's just going to be I is equal to 7 over 8 l squared. Now, if you plug in your numbers, then you have that I is equal to 7 over 48 times 0.500 times 1.00 squared. Now, I is going to equal to 7 over 48 times 0.500, and then I is going to equal to 0.073 kilograms times meters squared. Calculate the tension in the thread that supports the rod. So our tension is going to be this one. Tension is going to be acting up. So let's see, so you have positive y and our positive x. Now we have to find the torque from the tension. And we know that this is going to be a fixed support. If it's a fixed support, that means that we have torque equilibrium. And that means that the summation of the torque is going to be equal to 0. So then we can find the torque from the tension. So that means that torque from Ft, we can first find our lever arm. So RT, this is from the pivot to the end. This is going to be equal to 3 over L over 4. And then our torque is going to be equal to 3 times L over 4 times the T. The tension force. The tension force, you can see the tension force is perpendicular, which is why we call this equal to our Ft, or to our force perpendicular. Yeah. So then after this, we can find our torque from gravity from Fg. We know that Fg is going to act at the center of mass. So here is our center of mass, and mg, that's equal to the force of gravity. So we know that the gravity is accelerating the mass downward by 9.8 meters per second squared. So we can write this R of G is equal to L over 4. That is going to be the pivot distance. So that means that the torque of gravity is going to be L over 4 times mg. That's because this is also at 90 degrees, and Fg is going to be perpendicular because that's 90 degrees from our axis. So now after this, you can set them equal because you know the summation of the torque, because those are the two only forces that are, yeah, this is also 90 degrees, but these are the only two forces that are acting on this system. So that means you can set them equal to each other. So that means you can say that the torque of the tension is equal to the torque of the gravity. And because of that, we can write 3 times L over 4. T is equal to L over 4 mg. You can see that we can cancel out L over 4. So then we're just left with 3T is equal to mg. So now T is equal to 1 over 3 mg. Now if you plug in your numbers, that's going to be equal to 1 over 3, 0.500 times 9.8, which is equal to 1.63 newtons. The thread is cut so that the rod is free to pivot about the fixed pin. Determine the angular acceleration of the rod at the moment the thread is cut. So we know that from torque, we know torque is equal to inertia times angular acceleration. And we know that for our torque, we can write our torque as equal to R times your force that's perpendicular. And as we know that the perpendicular force is Fg, and we know that that is equal to mg. So that means that our torque is equal to L over 4 mg. Now, you can plug this in here. So our torque, L over 4 mg, is equal to our moment of inertia, I, which was, yes, our I, which we found up here. I use a different color for this. Use blue or green. We found our I up here, and we want to plug that in there. So our I was 0.073 times our angular acceleration. Now we want to solve for A. So we have, if we plug in everything else, our length was 1, and divided by 4 times mass of 0.500 times our gravity 9.8 is equal to 0.073 times our angular acceleration, 0.25 times 4.9. That's equal to 0.073A. That's 1.125 is equal to 0.073A. So your alpha is going to equal to 1.125 divided by 0.073. That's going to equal to 16.8 rods per second squared. Determine the angular momentum of the rod relative to the pen at the moment the rod reaches a vertically oriented position. So, we know that when it's vertical, that means the rod rises, the rod falls from horizontal to vertical. And when it goes from horizontal to vertical, that means when it was at a horizontal position, that it had gravitational potential energy, UG. And then when it's at the vertical position, then it goes into rotational kinetic energy. That's because earlier it was like this, right? It was horizontal and then it fell down. So it basically, it went clockwise. So earlier it was like this. This is our rod. Okay. So this was the rod initial, and this is rod final position. So this means that it was rotating this way. It was rotating clockwise. So clockwise is going to be equal to a negative torque, and we can use conservation of energy to represent this at these two different stages. So we know that if we have we can say we have conservation of energy. And because of this, you can write that the initial potential energy plus the kinetic initial is equal to the final plus the kinetic final. So we know initially that it had zero kinetic energy because it was not moving, and that it was held by the rod. So it was held by the tension, and it was not accelerating, so initially it was equal to 0. And then we know that the height drop was equal to L over 4. So then we can plug this in, rewrite everything. So we know that mg times L over 4 is equal to UF plus KF. So we know that we don't have any more potential because it can't go any further down. Because once it's like this, there's nothing to push it back up. So once it's at this final stage, it won't go back up. Because of that, then we know our initial is also, our potential final is going to be equal to 0 too. So then we know that our kinetic, we know it's all rotational. So we use the rotational form of kinetic energy, which is 1/2 I times omega squared. If we plug in everything, we have 0.500 times 9.8 times 1.00 divided by 4 is equal to 1/2 times 0.073 omega squared. So that's going to be 0.5009.8, 0.25 is equal to 0.0365 omega squared, 1.225 equals 0.0365 omega squared. Solving for omega squared, we have 1.225 divided by 0.0365. And omega is going to be equal to the root of this. 5, that's going to be equal to 5.80 rad per second. Now, we need to get our angular momentum. So that is going to be equal to L. L is equal to inertia times velocity, and an angular velocity. I we found earlier was 0.073, and our angular velocity was 5.80. So that angular momentum is going to be 0.42 kilograms times meters squared per second. Just as the ball reaches the vertically oriented position, it is struck in an on-head elastic collision at the lower end by a ball of mass m is equal to 0.5 kilograms traveling in a horizontal direction at an initial velocity of 2 meters per second. Determine the velocity, both magnitude and direction of the ball just after the collision. So that we know the mass of the ball. Let's write everything down again. 0.500 kilograms. Our initial velocity of the ball. So pre-collision. And our moment of inertia is from earlier. So we have elastic collisions. In our elastic collision, this means that we have conservation of energy. Because of that, we have 1/2 m v initial squared plus 1/2 I omega squared I. Actually, let's write so you have kinetic energy plus you have translational kinetic energy plus kinetic energy rotational is equal to kinetic energy translational plus kinetic energy rotational, and it's just like different amounts, so some of it will be transferred to the other form. So it's equal to 1/2 mv squared f plus 1/2 I omega f squared. So plugging in, we have 1/2 0.5 times 2 squared plus. So on the left side, we have the ball is 1.00. The rod is 1.23. And then that's going to equal to 2.23 times 0.025 plus VF squared 0.0365 omega F squared, and that's equal to this. Now, after this, we can use our conservation of our angular momentum. R times mass times velocity initial minus I times omega initial is equal to R mvf plus I omega f So this was just the torque minus the I times omega F equals to the torque plus the I times omega F. Now, a 0.75 minus 0.423 is equal to 0.375 VF plus 0.073 omega F. 0.327 is equal to 0.375 F plus 0.073 omega F. .62 meters per second, and that is going to be your answer. So what happens as a result is the ball